Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to continue to talk about lateral resistance of nailed connections. In the previous videos we looked at the geometry and the spacing requirements, and then in the second video we looked at what is the strength for just one individual nail in a connection in shear. And now we're going to look at how do we build up for a full connection, what is the total strength of a nailed connection. Okay, so this is the equation from the standard. It's the same in 14 and 19 as is most of the things that we're talking about in this course. So we have our overall strength, NR, capital NR, equal to the NU, which is basically the individual nail strength modified to account for our modification factors for duration, service condition, and treatment. And then we have number of fasteners, NF. So if I have 10 nails, obviously I'm going to have to multiply my strength for each individual nail by 10. And NS, which is the number of shear planes in the connection. So for 2 shear planes, I'm going to get double the strength, as we talked about in one of the previous connection videos. And then we have this catch-all modification factor, JF, which includes 4 different conditions that we need to consider. So we multiply all these things together and we get our total connection strength. Okay, so number of fasteners makes sense. Number of shear planes makes sense. Capital NU is just like when we have a lowercase f, like for example, when I have my tension strength FT. So here I have basically my individual nail strength NU, and I multiply it by KD, KS, FKT. We're very used to doing that. So that's like getting our capital FT from our small ft, for example, for tension design, and then I have my JF. But before I get to JF, I just wanted to remind you of how I define 3-member connection versus a 2-member connection. Okay, so a 3-member connection doesn't mean I have 3 members. Okay, it's counterintuitive. Okay, a 3-member connection by definition means that one nail, each nail, is connecting all 3 members. So if I have a connection that looks like this, I have my nail, goes all the way through 3 members, and I might have the next nail might be nailed from the other side, could be nailed from the same side. Okay, but each of those nails intersects 2 shear planes. Okay, by definition for a 3-member connection. So this one is a 3-member connection. And all 3-member connections will have NS equals 2, number of shear planes equals 2. Okay, all the Johansson yield equations for those 3-member connections assume that NS is going to be 2. Okay, then, but the other case that I could have is maybe I don't have nails that are so long. Maybe I am just basically having each nail go from one member into the center member, and I'm doing that from each side, for example, something like this. So now each nail only intercepts 1 shear plane. Okay, this is not a 3-member connection. This is 2 separate 2-member connections. So the NS, the number of shear planes for each one, is going to be 1. So basically I can design the one connection. I can design like the top part of the connection. Then I can design the bottom part of the connection. The only wrinkle here is I will have to satisfy the spacing requirements here for both sides of the connection simultaneously. So obviously these nails have to be spaced far enough apart that they're not going to cause splitting of the central member. Okay, so that kind of penalizes me a bit. Okay, so now what about all of these fastening factors? That is the factor JF. Okay, so JF is basically a multiplication of 4 different potential factors for strength of nailed connections. And they depend on JE is for end grain, JA is for toe nailing, JB is for nail clinching, and JD is like a system effect factor for shear wall and diaphragms. So I'm going to go through each of these one by one and draw some pictures to make them hopefully a bit clearer. Okay, so I've indicated the grain. So let's say I have these two pieces of wood, and then I want to nail them together, but the way that I decide to nail these together is I go from the end of this one and I nail into this other one. Okay, so I'm nailing basically into the end grain of the second piece. So this looks something like this. Here I have one piece, and I'm putting like this my second piece, and then I am nailing, if I can hold all these things at the same time, I am nailing into the end through this piece and into the next one. So you can see that in the embedded piece here, I am nailing basically right into the end grain. Okay, so I've indicated the grain directions here. So nailing into the end grain is not great, and we have to reduce our strength. Why? Okay, so if I have my bundle of straws here, okay, if I nail into the side of that bundle of straws, you know, I get good friction behavior here. Everything is held nice and tight. Now you can imagine that if I am nailing into the end of the bundle, okay, I don't want to go inside the straw, but in between the straws, okay, let me allow that to focus or something. It's a bit hard to see because of all the white. If I nail it into the end, then you can see that it is kind of easier to separate those fibers apart. So when I want to bend this in shear, I'm bending the fibers. And that is going to, you know, that mechanism has a lower strength. So if I nail into end grain, I'm allowed to do it. In this case, unless I'm doing withdrawal. Here I'm allowed to do it, but I have to reduce my strength. So if I'm nailing into the end grain, then I have to take this factor, JE, not JA. I need to take this factor JE into account, which reduces my strength by 1/3. And if I'm not nailing into end grain, then I just set JE equal to 1. Okay, so that's end grain factor. Next is the toe nailing factor. Okay, so let's say I'm doing something similar and I want to nail these two pieces together. But instead of nailing from the bottom up here, you know, like let's say that this is a stud sitting on a bottom plate and a light frame wall. Instead of nailing up from the bottom, what I can do is I can do a toenail, which means that I start at the side and I nail in on an angle. You know, if you've done any construction, you've probably done this before. It is a bit awkward. It's hard to get it exactly right. And there is actually a requirement for what the angle of this has to be. So this angle here is required to be 30 degrees. Now, I mean, you're not going to get a protractor out when you're doing this, but with practice, you know, you can get pretty close to 30 degrees. The other requirement is on length. So if my total nail length here, if I call that L, then I have to be 1/3 of L in the top, and basically the rest embedded in the bottom piece. I mean, it's not going to be 2/3 vertically because of the angle, the 30-degree angle. So if I do toenail like this, it's going to be stronger than nailing into end grain. And I will apply still a reduction factor, though, of 0.83 on my strength, because I'm not doing totally side grain kind of shear. Otherwise, we're going to use a factor of 1.0. Okay. Okay, so next one is the nail clinching factor. Okay, so this one only applies to 2-member connections. And so this is only 2-member connections. Okay, basically what I do is, you know, if I nail a nail through, you know, I can use a nail that is longer than I need to get just into the next member, right? So I can go a little bit longer. And furthermore, what I can do is, after I have that nail that is a bit longer, what I can do is I can take my hammer and I can bend down the point of the nail sideways. So basically I nail through, then I go to the other side, I get my hammer, and I hit the nail sideways. Like I smash the nail like this, hammer it, and then basically I tilt down the end. Okay, so what that does is it prevents withdrawal, and that makes the lateral strength higher, because if I now want to bend my nail, you know, when we talked about the rope effect, if I want to bend this nail, you know, as it goes down, it also has to come in, right? So as this thing bends down, the point here, although it goes down and it also comes in, right? Because it's moving on the arc of a circle. But if this is restrained by the clinching, then as it moves down, it is engaging this nail more and more in tension than it would have otherwise. So it provides even more strength on top of what we were already would be assuming for the rope effect, for example. So it holds everything together better, basically. So hammer down. Okay, so if I do that, then I get a 60% bump on my strength, and I only use that for 2-member connections. Okay, the last one is the shear wall diaphragm factor. Okay, so shear wall diaphragm factor accounts for the fact that if I'm building, you know, a shear wall, and I have my studs and I have my plates, and then I put plywood on top, and I'm going to use a whole lot of nails. And same thing for a floor diaphragm, where I have floor joists and on top I have plywood, and that plywood is nailed with a whole lot of nails. And so this is kind of like a system effect factor. Since I have so many nails, I'm reducing the variability of my response, and I'm getting closer to the mean. So that means I can bump my strength by 30%. Okay, so I just take all of those 4 factors, JD, JB, JA, and JE. I multiply them all together. That gives me JF. And JF is just the last factor on the end of my total load lateral resistance equation for nailed connections. And so once I have that, I have my total strength, and that's about it. So that's the whole process. First, I'm going to find my small nu, which is the individual nail resistance, and I'm going to check all of the modes that apply to either a 2-member connection or a 3-member connection, keeping in mind the definition of 2-member and 3-member connections. And then I'm going to modify that by KD, KSF, KT. Then I'm going to multiply that individual nail shear plane strength NU times NS for the number of shear planes, and then times NF for the number of fasteners, multiply it by phi reduction factor of 0.8, and then multiply it by JF, which accounts for all of those other phenomena that we just talked about. And after I'm done all that, then I have my nailed connection strength. And I just need to make sure that I satisfy my spacing criteria, obviously. Following up on this video, we're going to start talking about how do we calculate withdrawal strength for nails. So actually a nail that, how do I decide how strong it's going to be to pull the nail out of a piece of wood.